Aha. So your extra vector
Is actually
so let's see here, we got 1 minus 1, 0 is equal to what? The first column minus the second column, right?
yeah.
Which you can check is correct. Do you see how if you understand this, it's way faster than writing down equations? Like,
Yeah.
I mean, of course, this one you could probably just guess, oh, that's this minus this, right? But so this is part of a general algorithm, right? To decide if you want to see if vector v is an element of the span of W1, W2, WK, right? What do? You just look at the reduced row echelon form, or you don't even have to do that, right? But I mean, you don't have to be a slave to the reducing all the way to the bitter end of the reduced row echelon form. But the point is, if you look at the reduced row echelon form of that matrix, that will reveal to you whether or not V1 is in the span of those. See, because if after all of this V1 is a pivot column, it's not in the span. Because if this ends up being a pivot column, that means you've got a row of zeros with a 1 at the end, which corresponds to, like you can't build V1, you can't build a pivot column from other pivot columns. Okay, that's something that's kind of like a basic observation behind all of this. You can't build pivot columns from pivot columns, right?
Yeah, if you can build it, if it's a pivot column in the reduced row, it's not in the null.
Right. I mean, but pivot columns are like E1. I mean, what are the pivot columns? They're E1, E2,
Yeah.
E3, so forth. You cannot build E1 from E2. And they are independent.
Yeah.
So these are some tricks that I try to teach linear. Let's turn the page here, and if you do you still have a little bit of time? Or
Oh yeah.
trying to make up. We missed some. I don't know how we got behind. We're behind, but I'm trying to hit some of the greatest hits of linear algebra because I'm hopeful this somehow helps you with the GRE. We'll see. But let's turn over to linear transformations, okay? Because there's something similar that goes on there. So if we have T as a linear transformation from a vector space V to a vector space W, right? Then kernel of T will have some things in it, right? Generally speaking, let's suppose it's got V1, V2, VK, let's say, all right? That's going to be a subspace of V, right? And so let's see here. We're going to assume the dimension of V is n, and the dimension of W is, well, do I want that? Fine. I made, it is what it is. All right. I made my choice. Okay. So, let me call this thing here beta naught, right? So extend beta naught to beta equal to V1, V2, VK, VK plus 1, Vn, right? Basis for V. So let's see here. We have, let me draw a picture. Here's V, right? You've got some the kernel of T is a subspace of that, right? Then over here to T maps over to W, right? And in W, you have something called the image of T. What would that be? That would be T of X such that X is in V, all right? So what's the relation between the kernel, the image, and V?
So the kernel is inherently, everything in the kernel is in the image, for one.
Well, everything in the kernel maps to like 0 over here, right?
Yeah. Okay, so.
So definitely nothing in the kernel maps to whatever. If there's some, I mean, this has to be the span of some gamma, right? Let's call it the span of W1, W2, whatever. I don't know however many things are here. Let's call it S, yeah?
Yeah.
Whatever that is. Suppose that's a basis,
Yeah.
right? Those can't be formed from the image of the kernel, right? Because those just go to 0.
Okay. So.
What do you propose if we call this thing gamma? Do you have any intuition for how can we build a basis for the image?
For the image?
Yeah.
And that's the span of all of W?
It's the span of those. It's the F-linear combinations of, I didn't say what field we're working over, so suppose field F, you know.
Yeah.
It's not going to be all of W, no. And not unless the mapping's an onto map. There's no reason it has to be.
Okay.
That's why I drew W I drew image, you know, like it's a smaller, perhaps a smaller dimension space.
Okay. And.
What, yeah.
I think I have it, so just ask me the question one more time.
How should I form the basis for the image?
The basis of the image, like, I would do it by, wait, but you don't have that property. Essentially,
With what's given on the board?
The T of V's, V1, V2.
But T of V1 is 0, T of V2 is 0, right?
Oh, everything?
T of Vi is equal to 0 for I equals to 1, 2, ... k, because that's a basis. I said it out loud, maybe I didn't say it long enough. This is the basis for the kernel. So those things all map to 0.
So how would I build a basis for all of the, or for the image W, or just all of W?
Well, what about the things after it? What about the Vk plus 1 through Vn, yeah?
Yeah.
So those are not in the kernel, right?
Yeah.
So I would say let gamma be the image of those guys.
Okay.
So like T of Vk plus 1, and so forth all the way on out to T sub Vn. How many things is that?
N minus k thing, k plus 1.
Right, this is n minus s, so s is equal to n minus k, exactly. Okay.
But that doesn't inherently give you a basis, because we have too many things.
Oh, well, no, this is not a basis for W. This is a base. Oh, that's I mean, I think you can argue that this set is a basis for the image of T. Here's how. So, what's an arbitrary thing in T? T of X, right?
Yeah.
But that is T of the sum I equals 1 to n of Ci, Vi. By assumption, the V's form a basis for W. I mean, V.
Yeah.
So any X is a linear combination of those. But the thing is, everything in here, all the way up to K, gets
0.
killed.
Yeah.
So this just leaves us with the sum I equals k plus 1 to n of ci t of vi, which is an element of the span of gamma. See that these are things forming our gamma. So gamma is a generating set for the image of t. What remains to do, though, what remains is, why is gamma linearly independent? Just because it's a generating set doesn't mean it's a basis, right? Why is gamma linearly independent?
Well, we already took away the image, the zero stuff. So all we have to do is show why that they're not additions of each other.
Okay, so let's suppose that, the sum I equals k plus 1 to n of ci tvi is equal to 0, right? We'd like to show that that implies all the coefficients are 0. So that gives me that t of the sum I equals k plus 1 to n of ci vi is equal to 0, right? What does that say about that vector? Where is it?
It's in the kernel.
Right, yeah, so this is in the kernel. And what's kernel T built from?
Things that map to 0.
Right, but in particular span of V1,
Yeah, to VK.
VK, right?
Oh. Well, if they're not 0, I mean, if additions of them aren't 0, that means they're linearly independent, right? I mean, no, that means they're not. Yeah, they can't be built from each other.
Yeah.
So you're saying if we get anything that equals 0, it's already in there, but we suppose that it already wasn't in
Well,
there.
we supposed we took a linear combination of vectors and gamma and set it equal to 0 is what we supposed, but
Yeah, but that would imply
that implies, yeah, like
that you combine to get something in the kernel.
right, and also the kernel is the span of those vectors, right?
Yeah. So you added 2 vectors from this to get a thing in the kernel.
And so,
No, but if you added them to get 0, I don't think you can do that if they're independent, if they're linearly independent.
well, let me just put it this way. So we have some. I mean, I agree with you, but let me show you why. Ci vi, right? It's in the span of these, right?
Yeah.
So it's going to be equal to the sum I equals 1 to k of bi vi, right? For some choice of b's. But you can just move all of that to, you can just take this equation, erase this equals, turn it into a minus, set it equal to 0.
Yeah.
And then by linear independence of the basis, that implies all of the coefficients are 0. Therefore, C1 through CK plus 1 through Cn are 0, which is what we wanted to show.
Yeah.
So, but yeah, I always think of it in terms of, well, you can't build this from that.
Yeah.
And that's right. But how do we take it from a feeling to a proof, We use linear independence of the basis. Okay, so what do we have? We've just showed that the number of things and gamma is actually, what was it, n minus k. So what have we proved? We have proved that the dimension of V, which is equal to n, is equal to k plus n minus k, right? Which is what? The dimension, which is equal to the rank of T plus the dimension of the kernel of T, which is often written dimension of V equals rank of T plus the nullity of T. In fact, people will often call the kernel the null space or the null space the kernel. People just freely identify these words. I personally try to use null space for the matrix and kernel for the mapping. But I understand those folks who don't want to do that. But here you go. This is the mapping version of the rank nullity theorem. Now check this out. So if you, all right, so if we, I think I can erase all this. There's something neat to notice here that maybe I should show you it. Let me show you an example. So here's an example. Keep it relatively simple. T of f of x equals to f of x minus f prime of x. And here I'll let T be a mapping from third order polynomial, well, let's say quadratics to quadratics. So in other words, T of ax squared plus bx plus c is equal to, let's see here, ax squared plus bx plus c minus 2ax minus bx, yeah? Okay, so this is ax squared plus b minus 2ax. Oh, how did I get, that's just b, right? Dummy. Me, not you. Derivative of bx is just minus b, right?
Yes.
So plus c minus b. What's the kernel of T?
Definitely got 0 in there. Actually, you don't. The kernel of T are things like, oh, there's all the linear stuff. Oh, wait, no.
We need
Such that,
a equals 0.
yeah. Yes.
It could just be 0. That's annoying if that happened.
It could?
It
Oh, yeah, it could.
So a is 0. Oh, curses, it's just 0. This gives me a equals 0, which forces b to be 0, which then forces c to be 0. So it's just 0. Aw, man.
I didn't mean to accidentally guess the rain on your parade.
Son of a gun. All right, I know how to fix it. We'll do... Will that fix it? Oh, man. Dang it. Fine. All right, I'm going to be lazy. I'm just going to make it f prime of x, because at some point or another, Ginny's going to call and I'm going to have to apologize. It's a baseball night. So she will not be home anytime soon. So this is 2ax plus b. All right, there we go. A little bit easier to work with. What's the kernel of T? Your calculus knowledge already told you it was
0.
Not, well,
No, so a, 2ax plus b. So the only way you get that if a and b are 0.
okay, so if a and b are 0, we're just looking at
C.
C.
Constant polynomials.
Right. In other words, the span of 1, right? So if we use the basis, let's say x squared, it's kind of boring, x squared x1, right? And okay, so we have t. I guess I need to remind you the matrix of t, right? Matrix of t with respect to the beta basis, yeah? Times the column vector of the coordinate vector of ax squared plus bx plus c with respect to the beta basis, right? Is equal to this guy. So I'm not sure what we got put there, all right? This, of course, is ABC. So over here you got what? You got yourself a B, you got yourself a 2A, and you got, I'm an idiot, other way around. I put the x squared first, right? So 0, 2A, B, because of the ordering of the basis. So what has to go there then?
0's on the top.
Yep.
2, 0, 0.
Sorry, I'm having a,
0, 1, 0.
yeah. So I've forgotten something. It's not wrong what we're writing. I'm searching for my my thought here. So what if we instead use the basis gamma x squared x over 2, or rather not x over 2, 2x 1. Oh well, I got to be careful here. And then okay, but let me be more careful here. And we're looking at t, not beta beta, but beta gamma. All right.
Let's see.
So here, to figure that out, I would have. Let me write a separate calculation over here. So I would have the matrix. We're trying to figure out what it is. All right. So the coordinate of in the domain ABC, right? If I use basis x squared 2x1, right? So I've got 2ax plus b with respect to the gamma. What's the coordinate vectors of that? Well, gamma, I've still got 0 for the x squared piece, right?
Yeah.
But I've got how many 2x's?
1.
Not 1, but a and b.
Yeah.
So you see the difference? Now the coordinate vector is 0ab versus 2ab.
Yeah, so you get zeros on the top again. 1, 0, 0.
Mm-hmm.
0, 1, 0.
Right.
Yeah.
So this is an example of the the straightening theorem. I wanted the I want the 1 to go. See, Audric, what I want is like I don't know why. I just want that matrix. Can I make that happen? Or would I choose gamma equal to what to get that?
1, 2x, x squared?
1, 2x, x squared.
Yeah, I think so.
Because then, let me call it gamma bar. So 2ax plus b, gamma bar coordinates. I've got 0 of these guys, 0 of the, oh, no, I got a b.
Yes, that gives you 1, 0, 1.
I think I want, oh, I'm sorry.
0, 1, 0, yeah.
Oh, 0, 1, 0.
Oh, wait, on the first, I'm talking about the first row.
But I'm trying to figure out what coordinate this gives. Oh, yeah, I'm sorry. My bad. So what's the, like you said, b?
Yeah. That you want, and then 2ax.
A, right?
Yeah. So you get 0, 1, 0. No, but that'd give you an x squared. You need to flip.
Would that give me x squared? Because I got 0.
Oh,
So this means, in terms of the gamma basis, that means I've got b times 1 plus a times 2x plus 0 times x squared is equal to my vector.
yeah.
And that is, I mean, this is
That matrix right here?
My point to you is,
Yeah.
if I use that basis,
Yeah.
right, then, all right, so if I've got matrix, I'm not changing the beta basis, right? The beta basis is staying fixed. I'm just
Yeah.
messing with the range basis. And with that choice of, I get b, a, 0, right?
Mm-hmm.
And so to make it so, I need 0, 1, 0 to get that.
Yeah.
And then I need 1, 0, 0. Wait a minute. I'm an
Yeah,
idiot.
see what I'm saying?
Oh, curses.
I think you need to flip like 2x and 1 or something.
Oh, so I need to flip.
I'm not sure which one just yet. So for that one, you'd have to have 2x in the middle. You need to flip 2x.
I already
x
tried
squared.
that. Flip the 2x and x
I
squared.
think that'll fix it. Let's see what order matters now.
Yeah. So
So
that,
you get a 0.
well, that would give us whatever here.
Wait. I'm sorry, I don't know.
B,
Yeah.
0, A.
Now you get a C.
So I get a B, 0, A. What will that do to us? Then that puts a 1 here. No, excuse me.
That first one stays the same, 0, 1, 0.
Sorry. Let me finish this thought here. So, 0, 1, 0.
Yeah. I think you run into trouble with this one.
And then to get the 0 in the middle, we need zeros.
Yeah, so that already messed it up.
And then that puts,
1.
oh, excuse me, puts it here, right?
Yeah.
So I guess I can't.
Oh wait, why would? Yeah, that doesn't make sense because if we kept this basis the same, you'd always get a 1. Like you can't get that matrix without getting a C. At the end, you can't have a thing in the last column because of how it's ABC. You know, it means we have to get a C. And there's no C minus C.
So we'd have, what that means is we have to change. So if we wanted that to happen,
The ABC.
we're gonna have to change this as well, right?
Yeah.
So if we let beta bar So I want the kernel thing to come first, right?
Yeah.
So the kernel, which was what? 1, right? 1 differentiates to 0. So I do 1, and then, I mean, it doesn't matter. I guess I can do x squared x. So the beta coordinate of ax squared plus bx plus c is what? It is c a b, right? So we do, chalk is too good. CAB,
You want that matrix? I don't think that gets you that.
no, that's this to get me, and what's the,
You get 0.
I'm still using,
0, 0, 1.
I'm still using the, am I still using the gamma bar? Well, anyway, you tell me what to make gamma bar here in our quest for matrix madness here.
Gamma bar. So to get this.
I want target. We want this, right?
Oh yeah.
What should we make?
I don't know if you. Gamma bar should be.
I'm gonna erase this.
Yeah, gamma bar should be. I'm trying to think. That would be. So, 0, 1, 0 will give you A, so it'd have to be X first. Maybe 2X, I'm not sure.
2x.
And then 0, 0, 1 would have to be 1.
I bet it's the x. Oh, it's the 1.
Yeah, I think it's 1. And then X squared. And so that put B.
Okay, so what? Let's just for a second here. So we got ax. Excuse me. We got the image was 2ax plus b. What is the gamma bar coordinates of that? It's a, b, 0.
I think that's wrong. Yeah, wait.
I think we got it. Got it.
Yeah.
So
Yep.
0, 1, 0, 0, 0, 1, 0, 0.
Nice.
So yeah.
Okay.
So basically, by what I'm trying to point out to you is by manipulating the order of the domain basis and the order of the range basis, you can move the identity matrix in your matrix representation wherever you want, essentially. You notice what's going on. What's producing the ones here? What kind of basis are we using, right? If you check it out, what we're really doing is we're using t of x squared and t of x. This is 2x, this is 1. It's not an accident. That's the basis that you need. That theoretical basis we were dealing with, the gamma thing, that is exactly the basis which will give you, if you order it in the right way, a copy of the identity, a rank by rank identity matrix, padded with zeros. So if you want to classify, what does a linear transformation look like, right? If you want to classify, what does a linear transformation look like from, one vector space to another? If we have T going from, say, V to W, and you want to say, okay, so like I can put a basis beta on here and I put a basis gamma on here. I'm free to pick them however I want. Well, basically, you can make the matrix of T with respect to beta gamma look like, the identity matrix with the rank, let's say rank R, I'll say R, padded with zeros, where R equals the rank. Well, it's the rank of T which is the dimension of the image of T. So it's kind of, in some sense, it's kind of boring, right? Like, you can always choose the basis for your domain and range to make the matrix look like that. So the question of whether, if you have two mappings, right? If you have two mappings, say T1 and T2, both from V to W, are they the same map? And so I mean that in a somewhat sort of esoteric sense, like, are they kind of the same map, just as a question, like essentially the same map, just with a different choice of notation? Well, that kind of boils down to whether or not they have the same rank. Now, what we'll talk about next time is the much more difficult question of when we're not allowed to adjust the basis in the domain and the range separately. See, if instead of going from V to W, we look at linear transformations from V to V, a so-called endomorphism, right? And if we have to use the same basis here as we do there, then we can't play. See, we were just playing this game where we adjust the input and adjust the output separately, right?
Yeah.
Well, now the input and output knobs are they're linked, and so we're stuck with it. And then the question is, how do you look at a linear transformation V to V, and if you're going to pick a basis, how do you discover like the quintessential form of the linear transformation, right? How do you decide whether, if you have two linear transformations, say T1 and T2, both from V to V, that they're really the same transformation, just perhaps using a different ordering of the basis or something, right? Like maybe the formula for T and the formula for T1 and the formula for T2, they look different, but maybe there's just a change of coordinates that takes one formula to the other, you know? How do you decide whether or not that's possible? It turns out that basically for that to be possible, they have to be related by a similarity transformation. Because if you change coordinates on the matrix of such a thing, if you use like beta, and you look at it with respect to another basis, you end up with something like this: P inverse T beta bar P, right? So this is a similarity transformation. So if we have two linear transformations, so suppose you have a fixed basis, but you have two different transformations. You've got T1 and T2. You could say that they're really just different coordinate versions of the same formula if they were similar matrices. So the question then becomes, how do you judge whether or not two n by n square matrices are similar or not? So we say A is similar to B if and only if B is P inverse AP for some P in GLN, the invertible n by n matrices. Now this is a formidable problem at the level of undergraduate linear algebra, but the answer to this is ultimately given by what's called the Jordan form. Two matrices are similar even if and only if they have the same Jordan form up to ordering of the blocks. So there's a beautiful and elegant answer to this question, but it'll take us a while to really appreciate it. The entry level to this discussion is, the basic form of the Jordan form is when the matrix is when the transformation or the matrix is diagonalizable. Right, and that brings us into the story of eigenvectors. To get to the Jordan form, we have to talk about generalized eigenvectors and all that. All of that said, there's a more generalized version of this in chapter 12 of Dummett and Foote. 12? Yeah, well, we're in where? Chapter 11? Chapter 12 of Dummett and Foote, where he looks at something called the Smith normal form. And so we'll also have to talk about that. And I'll try to put these things in an order which is useful to you. But sorry to give you a lightning review of a big chunk of linear algebra, but I figure
That's good.
we could use of our time. Hopefully Isaac has won his baseball game by now. I can leave this. I'm going to leave this. I guess I should probably turn off the camera. I hope my battery's not run out of... I'm not really sure how long these AAA batteries work, you know.